Welcome. In this video, we are going to derive the equation of an ellipse. So yep, we are back to Proofville. So if you refer to question 4 from the TI Inspire lab that we finished, we know that if we're given this picture where F1 and F2 represent the different foci of the ellipse, O represents the center of the ellipse, and P is a point on the ellipse. It happens to be a y-intercept. It doesn't have to be. But what we know that it's easy to see from this picture is that if I take the distance from O to P and square it, and I take the distance from O to F and square it, that it's going to equal the hypotenuse from P to F2 squared, because this right here is a right triangle. So if I take on the other side, it would also follow that if I take OP squared and add to it OF1 squared, that distance, it's going to equal also the distance from P to F1 squared, because that would be the hypotenuse. Here's something we also know from that lab. We also know from question 3C that if we take the distance PF1 and add to it the distance PF2, so I'm adding these two distances, that it is some type of constant. And we learned that that constant is equal to the distance of the major, or in other words, the longer, axis. So to write this out verbally, if we say, or what we learned from that question, is that the sum of the distances from a foci to a point on the ellipse, this is equal to the constant, or the distance of the major axis. So again, we're saying that if I take this distance right here plus this distance right here, it is equal to this major axis from this point to this point. Here's what we're going to do in the next part of this proof. We're going to take the center, which we defined at the variable or the letter O, and we're going to specifically put that on the origin. So let's consider an ellipse with the center at the origin. And I know this is not God's gift to drawing an ellipse, but I've drawn this about 17 times trying to record this, so it is what it is. All right, here we go. We're going to use the traditional A, B, and C variables that we used with Pythagorean theorem, but we're going to kind of use them in a different way. We are going to define this distance from the origin to this point on the ellipse as B. That's a distance of B. We're going to define the distance from the center to a vertice as A. Now, I know this isn't the most scientific, but just for presentation purposes, we're going to define each of the foci. Instead of using the variable F, we're going to define it at C. So the distance from the center to a foci is considered C. So let's kind of go back. What we remember, or what we knew from question 3C, is that if I take the sum of the distances from a point on the ellipse to a foci, we know that it is equal to the distance of the major axis. So if I take the distance from a foci to a point and take this distance, it's going to equal the major axis. So what does this look like using the letters A, B, and C? Well, notice how we have a right triangle here. And instead of using A squared plus B squared equals C squared, because we've defined our A's and B's and C's to be different, if you think about what Pythagorean theorem means, it means you take the side of a right triangle and square it, you add another side of a right triangle and square it, and that's going to equal your hypotenuse squared. So if you want to solve this in terms of your hypotenuse, you need to square root both sides. So a hypotenuse is equal to the square root of a side squared plus a side squared. Well, if I want to define this distance right here, based on the picture that I have, well, one of my sides is a distance of B. So this hypotenuse right here is going to equal the square root, one of my sides B, and my other side, remember this distance from here to here is C. So this hypotenuse can be defined as the square root of b squared plus c squared, where b represents the distance from a center to a point on the ellipse, and c represents the distance from the center to the foci. Well, the way that I have this picture set up, these two right triangles would be the same, so that means this side is also going to be b squared plus c squared. So again, if I refer back, where I know from our Inspire lab that the sum of this distance plus the sum of this distance equals the entire major axis, that means this distance of the square root of b squared plus c squared plus this distance, which is also b squared, square root of b squared plus c squared, has to equal the entire major axis. Well, we defined half of the major axis, which is called the semi-axis, to be A. So that means this distance must also be A, so the entire distance of the major axis is 2A. Well, these are like radicals, so I have two of them. I have two square roots of b squared plus c squared. If I divide both sides by 2, I'm left with the square root of b squared plus c squared is equal to A. And if I want to get the square root out of there, I can square both sides, and so b squared plus c squared is equal to a squared. So again, b, c, and a don't represent the traditional sides and hypotenuses of a right triangle. B represented that distance from, or half of the minor axis, the distance from the center to the point on the ellipse. C represents the distance from a center to a foci, and A represents the distance of a semi-axis. So just for future reference, I just want you to see when we do the proof, sometimes we'll need to have B solved. So remember that if I manipulate this, if I subtract c squared from both sides, that b squared is equal to a squared minus c squared. And then also know that if I need to know something about the foci, that c squared is equal to a squared minus b squared. So we are going to be using these two forms a little bit later on in our study, and I just want you to understand where those come from. So now for this last part of the proof, we are going to be in some algebra help. Here's what we're going to do next. We're going to take this exact same picture. So I'm just trying to get you to understand where we've come from. We did the TI Inspire lab, where we just defined these points to be generalities, foci points, point on the ellipse, and a center. Then we put that center on a coordinate plane at the origin. And we talked about these distances A, B, and C. Those distances are not going to go away, but we're going to kind of look at those maybe just a little bit differently. If I take that same picture, okay, and again, I know my ellipse is less than desirable, but we'll just work with it. Instead of calling this a point P, like we did here on the Inspire lab, we called this a point P. Now I want to define it as a point XY. Okay, my center here is now 0, 0, and I am just naming one of my focal points as C. Okay, so you can kind of see how that's going along there. All right, we defined the distance earlier from 0 to this point as B. Well, if I think about this in terms of an XY coordinate, now this is the distance of Y. Next, we call this distance C, and it still is C. But if I think about this distance right here, this is now the distance of X plus C. Then the focus point on this side, since they're equidistant, is going to be X minus C. So when I think about this distance right here, I can think about this distance right here as being the square root of X minus C squared plus Y squared. Remember, this is the side, I'm just using Pythagorean theorem, X minus C squared plus Y squared, and then I take its square root in order to find that hypotenuse. And then this side would be the square root of X plus C squared plus Y squared. And as we learned from the previous work that we did, it's equal to the major axis, and my major axis is still 2A. So basically what I did is I redefined B to be just the Y coordinates, and I redefined C. Instead of just calling it the length C, I am using coordinates. where this distance is x plus c and this distance is x minus c. So that's all I did. I'm just rewriting this step that we did earlier in terms of x's and y's so that we can derive our equation of an ellipse. Okay, so this is going to equal 2a. All right, are you ready? Because this is probably going to take even more paper, so follow along. All right. What I can do next is, if I wanted to square both sides, this is going to be way ugly. So I'm going to take this term right here, and I'm going to subtract it to the other side. So I am going to be left with the square root of x plus c squared plus y squared equals 2a minus the square root of x minus c squared plus y squared. Then I can square both sides. Okay. So in squaring both sides, I am now left with x plus c squared plus y squared because the square root and the square cancel. And then this requires you to write it twice in FOIL. So when you take 2a times 2a, I would get 4a squared. Okay. Then I have another square root business. So when I take 2a times this square root business, and then 2a times this square root business, you get two of the same sign, or two of the same term. So I end up with 4a, the square root of x minus c squared plus y squared. And then when I take the square root times the square root, they cancel, leaving me with a positive x minus c squared plus y squared. Okay, next, notice how I have, let me focus this a little bit better. I'm looking at my screen. All right. So notice how this y squared and this y squared, I have one on both sides, so those can go away. So what I am left with next is x plus c squared equals 4a squared minus 4a times that square root plus x minus c squared. Okay, here's what I'm going to do next. I need to isolate this square root. That is really what my goal is next. So yes, the square root unit from last year is coming back to haunt you. I'm going to bring that over to the other side. So that's going to yield a positive 4a times the square root of x minus c squared plus y squared. So again, I took this term right over here, plopped it to the other side. I'm going to rewrite 4a squared. Then I'm going to subtract this to the other side and then rewrite that term plus x minus c squared. Okay, next I'm going to FOIL those two out. So I'm going to rewrite the left-hand side. So I'm up with 4a times the square root of x minus c squared plus y squared equals 4a squared. Okay, now this is x squared plus 2xc plus c squared, and when I distribute the negative, I get minus x squared minus 2xc minus c squared, and then plus x squared minus 2xc plus c squared. So notice what happens here. The minus x squared and the plus x squared cancel. The minus c squared and the positive c squared cancel. So what I'm left with is 4a, the square root of x minus c squared plus y squared equals 4a squared minus, and I can combine like terms, 4xc. Both sides are divisible by 4. So I am left with a times the square root of x minus c squared plus y squared equals a squared minus xc. So now I'm going to square both sides to see if I can get that squared out of there. And now what I'm left with is a squared times x minus c, the quantity squared, plus y squared equals, and if I write that out twice and FOIL it, I get a to the fourth minus 2a squared xc plus the quantity xc squared, so that is x squared c squared. Okay, so I'm going to have to shift to a new piece of paper here momentarily. All right, what I'm going to do next is I'm going to FOIL that out. So I am left with a squared times x squared minus 2xc plus c squared plus y squared equals a to the fourth minus 2a squared xc plus x squared c squared. All right, now let's distribute the a squared. So I'm going to have a squared x squared minus 2a squared xc plus a squared c squared plus a squared y squared. And all I did was distribute. And that's going to equal a to the fourth minus 2a squared xc plus x squared c squared. I didn't do anything to the right side. Well, if you notice, both sides have a minus 2a squared xc. So those can go away. And now I'm going to rearrange some terms again. I'm going to rewrite this a squared x squared term right here. But what I'm going to do next is I'm going to take x squared c squared and I'm going to write it on this side, and you'll see why shortly. Then I'm just going to carry down the a squared y squared. Okay. On the other side, I'm going to keep a to the fourth, and then I'm going to move this term over here. So when I move it to the other side, it's going to be subtracting. So on this side, if I look at these two terms, I can factor out an x squared. And I'm left with a squared minus c squared. On this side, I can factor out an a squared, and I'm also left with an a squared, and that should have been a multiply. I'm so sorry. That right here should be a squared c squared. That was just the two. So a squared times c squared. So when I factor that out, when I factor out an a squared, it should be a squared minus c squared. And let's go back. From the previous work, remember how I told you we might need different forms? Well, b squared can be substituted in for a squared minus c squared. So this right here is equal to x squared b squared. And I can substitute in b squared for a squared minus c squared. And yes, friends, we're almost done. If I divide every single term through by a squared b squared, what we develop is the standard form of an ellipse. Here, the b squares cancel, so I'm left with x squared over a squared, plus here the a squareds cancel, y squared over b squared, and that is equal to 1. So what this does is this yields the standard equation of an ellipse with a center at the origin. And here's what's important. Where the foci lie on the major axis. Okay, so to clarify, if this is my equation of ellipse, we know that A represents the semi-major axis. We know that B represents the semi-minor axis. So what this tells me is that I have a longer horizontal axis and I have a smaller vertical axis for my ellipse. Okay. If the standard form was x squared over b squared plus y squared over a squared equals 1, A still represents the semi-major axis. B still represents the semi-minor axis. So this means I would have a shorter horizontal and a longer vertical, so I would have an ellipse that looks like that. Then if I have my other standard forms of an ellipse, if the center was not at 0, 0, it would look like x minus h squared over a squared plus y minus k squared over b squared equals 1 if I had a center other than, if I had a center other than 0, 0 with a major horizontal axis. Okay, so I would have a longer horizontal and a shorter vertical. And then if I have x minus h squared over b squared plus y minus k squared over b squared equals 1, this is a center at hk, or other than 0, 0. So here my center would be hk as well. And I just made a mistake. This should be a squared. Okay, sorry, I've been recording too long to re-record. Okay, so to clarify, x minus h squared over b squared plus y minus k squared over a squared means I have a center at hk, and I have a major vertical axis because a represents the semi-major axis, b represents the semi-minor axis, and this would be a picture where I would have a longer vertical and a shorter horizontal. Now you're ready to look at some examples of an ellipse.